MBA 633 instructional video prepared by Professor Amit Dada, School of Management, George Mason University. In this clip, we will conclude our discussion of descriptive statistics by talking about outliers, the shapes of certain data sets, and a couple of important rules. Now, let's start with relative location. We've discussed measures of location like where's the middle, where are the quartiles, and so forth. We've also talked about measures of dispersion like standard deviation and so forth. Now, when you're trying to determine whether a value is very far away from the middle or not so far away from the middle, then units matter. So, for instance, we saw for these monthly salaries for the 111 students, the first value, the first student was about $300 below the mean salary. Now, is that $300 too much or too little? Is he very far away from the middle or not? So it helps to have some kind of standardization or relative position relative to the middle. So this is the all-important z-score. So every data point that you deal with is associated with what is called a z-score or a standardized score. And the way you compute the z-score is very simple. You measure how far a value is away from the middle, but you measure it in standard deviation. So let me show you how the calculation is done first. So the z-score for the first student, whose salary is $3,330, is simply 3,330 minus the mean. This is how far the student is away from the middle, but we want to standardize it. We don't want to measure it in dollars. We want to measure it in standard deviation. So we divide it by the standard deviation, because if the standard deviation is $650, then being $300 away may not be that bad. Whereas if the standard deviation is $200, then being $300 away means something completely different. So we have a value over here which is minus 0.47. So any negative z-score means that the value is below the mean. Any positive z-score means that the value is above the mean, of course. So let me, before I copy this formula down to the other values, let me standardize. Let me sort of make the addresses absolute here for these couple of addresses. Okay, so now I will copy this formula across to all 111 values. And now I can see how far each value is away from the mean in relative terms. For instance, student number 4 has a salary of $3,855, and I can see from the z-score that it is 0.33 standard deviations above the mean. Not a whole lot above the mean, but above the mean. Whereas if I look at student 11, it's 1.4 standard deviations above the mean. So these z-scores give you a sense of how far a value is away from the mean, relatively speaking. And then in a few minutes you will see that you can assign a likelihood to these values. So in other words, how significant are is this deviation away from the middle. So let me first write down the formula for the for the z-score that we just computed. So for any value, in order to compute its z-score, all you do is take the value, subtract it from the mean, and divide it by the standard deviation. That's how you get the z-score. Okay. So now there is a very useful rule called the empirical rule, which tells you that if the distribution of values, in this case, for example, we have the salary as the variable that we're looking at. If the distribution of salary is relatively symmetrical, in other words, the values are, if you look at this pattern over here, if the values of salaries are sort of evenly distributed around the middle, symmetrically distributed around the middle, bell-shaped like you see over here, then there is something called the empirical rule that one can use, which says that if you go one standard deviation away from the middle on either side, then the area between plus or minus 1 standard deviation will include roughly 68% of all the values in the data set. If you go out 2 standard deviations, that will include about 95% of the values. And if you go out 3 standard deviations, that will include 99% of the values. Now this is a very useful rule to remember, and later on when we get to something called the normal distribution, you will understand where this 68%, 95%, 99% comes from. But so just remember for now that if the pattern of values is relatively bell-shaped, in other words symmetric and bell-shaped around the middle, then roughly speaking within plus and minus 1 standard deviation will include 68% of the values, 2 standard deviations 95, 3 standard deviations 99. Therefore, we have this rule of thumb which says that if you have a z-value that is either greater than 3 or less than minus 3, then we call it an outlier, because as you can see from this 99% that it's in the extreme 1% of value. So it's considered an outlier. So the rule of thumb is, in order to determine whether you have any outliers in your data set, you first standardize the values. In other words, get the corresponding z-values, and if you have any z-value that lies beyond plus or minus 3, that would be considered an outlier. Now if I scan through the z-values that I have for this data set, for this variable monthly salary, I don't seem to see any values that are beyond the plus or minus 3. We have some that are relatively far apart. For example, this one's 2 standard deviations out, student number 70, and then student number 71 is also quite a ways out. But I don't see anything. Oh, we do have an outlier. Student number 84 is 3.08 standard deviations above the mean. That would be considered an outlier. In this case, it's an outlier that's above the mean. If you had a value less than minus 3, then of course it would also be considered an outlier. So that's the concept of an outlier. Now, what if the pattern of values, the distribution of values, is not symmetric and is sort of skewed like you see over here? Then you can use something called Chebyshev's inequality, which says that if you go within plus or minus z standard deviations away from the mean, then you will have at least at 1 minus 1 over z squared percent of the values will be contained within plus or minus z standard deviations. So if z were 2, in other words, if you were to go 2 standard deviations away outside the mean, away from the mean on either side, then that range, so plus 2 minus 2, if it's 2 standard deviations below and 2 standard deviations above, if you go within this range over here, and you can see that the pattern is not symmetric, then Chebyshev's inequality says that you would have at least 1 minus 1 over z squared percent of the values would be included in that range. So in our case, that would be 1 minus 1 over 2 squared, which is 75%. And this is a very powerful result. It's saying that regardless of the shape of the distribution, okay, it's saying that I can give you a lower bound. I can tell you that at least 75% of the values will be contained within plus or minus 2 standard deviations. So you can see that this is consistent with what we saw with the empirical rule. And remember, the important words are at least. So if the distribution is not bell-shaped, then Chebyshev's inequality gives you a lower bound. Now, the last item that we're going to discuss briefly here is the shape of the distribution. How do you know? How can you quantitatively tell whether a distribution, a pattern of values, in this case, for example, the pattern of salaries, we can eyeball it, of course, but is it possible to quantitatively state whether the pattern of values is bell-shaped, is it symmetric, Is it slanted in one direction or another? The technical term for this is skewness. So is the distribution skewed or not? And there is a built-in function in Excel to tell you what the skewness is, and that built-in function is skew. So I will use the built-in function skew, and I simply highlight the entire set of salaries, and we have the skewness over here, which is 0.54. So what does that mean? If the distribution, if the pattern of values is completely symmetric, is exactly symmetric, then you have a skewness of 0 or something close to 0. So any skewness which is close to 0 means that the pattern of values is symmetric about the middle, about the mean. If you have a positive value for skewness, like you have over here, 0.54, that means the pattern, the distribution is skewed to the right. It has a tail to the right-hand side. And if you have a negative value of skewness, then that means that the tail is to the left. You have a left skew. Okay. So in our case, if we look at this particular distribution, you can see that the tail is to the right, and that's why we had a skewness value which is positive. As a general rule, if you have a skewness value which is outside of plus or minus 1, in other words, the skewness is more than 1 or less than minus 1, we generally say that the pattern of values is not symmetric, and we shouldn't be using this empirical rule, the 68%, 95%, and 99%. So I hope you understand now what we mean by outliers and where this empirical rule, why it is useful, and why any value that is outside of 3 standard deviations, provided of course that the distribution is symmetric, any value that's outside of 3 standard deviations is considered an outlier because it's in the extreme 1% of values.